So, because groundwater is such an important resource for humans, because it is most of the available fresh water on Earth, problems that arise with the contamination of groundwater and some of the surrounding area are really important and a huge sector of where geologists work, really, because humans all need water. And one of the things that can happen as a result of too much groundwater withdrawal is a problem called subsidence. Subsidence occurs when basically an aquifer becomes dried out over time. You can think of an aquifer as a very thick sponge. As water is pumped out from wells, that sponge will dry out. And if you can think about like a sponge that you might use for cleaning, when it's full of water, it's thick and it's buoyant. And as it dries out, it gets thinner and it kind of curls up. And the same thing can happen with rock layers. When you're sucking out too much water, the aquifer will shrink and then all the land above it will also subside or decrease in elevation. And there's nowhere on Earth that I'm aware of that has bigger subsidence problems than the San Joaquin Valley in California. The San Joaquin Valley is beautiful. So in California, here's the coastal range, and then here are the Sierra Nevada mountains. The San Joaquin Valley is the area in between. It's flat, it has incredibly rich soil, and most of the fruit in the United States is actually grown in the San Joaquin Valley. Artichokes, strawberries, all sorts of berries, really all sorts of fruit and vegetables, broccoli, heads of lettuce are all grown in the San Joaquin Valley. And it's not a particularly wet environment. And all of that agriculture requires tremendous groundwater resources. So the San Joaquin Valley has been struggling to be able to not to slow its subsidence rates, because this is what was happening in the San Joaquin Valley. So here's a telephone post that has sadly been removed, but this is where the elevation used to be in the San Joaquin Valley in 1925. Due to rapid groundwater withdrawal, the whole land dropped to this elevation in 1955, and this was the elevation in 1977. So in a 30-year time span, the elevation dropped about 30 feet. And that rate actually was accelerating a few years ago when California was in a major drought. So subsidence is reversible. If we stopped withdrawing so much groundwater from the groundwater system, again, that sponge would fill back up and the land would rise back up too. So groundwater subsidence is something that is absolutely closely monitored in California. There's a video link here, which is honestly very depressing, and it follows California during the drought if you're interested in watching it. But I'm telling you, it is a downer. So subsidence, again, big problem for people who are building and living in areas where groundwater withdrawal is excessive. And every aquifer is a little bit different. So some aquifers will recharge faster than others. So you can take more out and some recharge a little bit slower. That really depends on the characteristics of the aquifer and on the local climate. Okay, another issue in coastal regions related to groundwater is saltwater contamination. So in an area that is along a coast, there is a lens of fresh groundwater. And then beneath the ocean, there is salty groundwater. And at some point, that variation between saltwater to freshwater, there is sort of a contact or a lens where the fresh and salt groundwater mix. And so this is actually a really good example of something that was happening for a long time on Long Island. Long Island is pretty much full of glacial sand. It's built on glacial sand. And what was happening was there's actually a fair amount of agriculture on Long Island. I know a lot of people think of the west coast of Long Island as Queens and the east coast as the Hamptons, and that's true. But a lot of the central portion of Long Island has plenty of agriculture. There are wineries there. There's a lot of horse farms there. And both of those have pretty extensive groundwater requirements. So there was a lot of withdrawal of fresh water for that and also to sustain a population. But it has an impact on the fresh and salt groundwater lenses. So excessive pumping on that fresh water can actually draw the salt water up and into wells. So that's what you see here, where you see a well that is pumping, initially was pumping in the fresh groundwater, but eventually began drawing in salt groundwater. So you can't put salt water on crops, you can't feed it to horses, and so for that reason you have to kind of abandon the well. You can see that this well again is being pumped because there is a small cone of depression right near the well where it comes into contact with the groundwater. So my friend Irene, one of her first jobs was when they stopped pumping on the aquifers around Long Island, and instead they let it kind of return, and it will return over time into its natural state. And so she traveled for one summer all along Long Island, monitoring and taking water samples from wells at various depths to figure out where was this transition between fresh and salt groundwater along the island. And they actually mapped it out to understand a little bit more about the response time of the aquifer. It's very cool. So groundwater is something that all people can really be trained to do. It's really just measuring water depth and collecting water samples and sort of continuously monitoring where you need to do. So lots of people, when they first either get out of an undergraduate degree or a graduate degree in geology, end up becoming what are called water monkeys, because it's pretty easy to do. But it gives you great firsthand experience at environmental consulting. It's pretty cool. So groundwater contamination is also a huge problem. There's lots of different things that can contaminate groundwater. Sewage is a great example of one. And this is a fantastic story. So this is a diagram of a house in a rural area. Lots of houses in rural areas use well water. And also, lots of houses in rural areas do not have access to sewer systems, and they use what are called septic tanks. Septic tanks basically are buried tanks in a yard, and all water from all the drains in a house will empty into a septic tank. Then the water, which is called the effluent, that water will leach out of the septic tank and just kind of flow downhill and become part of the groundwater. While all the solids that come out of all the drains in a house get collected in the septic tank, and depending on your usage, every few years you have to have the septic tank pumped and all of the solids removed, and that is a nightmare situation. All of that is well and good so long as your direction of groundwater flow doesn't reverse. So here again, small house, they have small water requirements. You can see a very small cone of depression here. And everything is good. The septic tank is emptying downhill, and most of the water is coming from uphill. However, if the neighbor next to them were to begin pumping heavily, that can change the direction of groundwater flow. And this actually happened to this woman I know, Judy. Her aunt lived in a rural area really close to the Pennsylvania border, and the adjacent property began to hydrofrack, which we'll talk about, I think, on the next slide, actually. And they began to heavily use water. So what that did is, when a well is heavily pumping, whether it's for irrigation or for hydrofracking, which I just mentioned, it creates a very large cone of depression, which is what you see there. And it reversed the direction of the groundwater in this area, and the effluent that was coming out of the septic tank instead reversed flow and contaminated Judy's aunt's well. And she discovered that later when she had E. coli because she was having tremendous stomach problems, and it turned out that her well was actually infected with human fecal bacteria, which is absolutely horrifying. But there you have it, human sewage infecting a well. Less dramatic, but certainly a bigger problem, is fertilizers. So farmers are pretty heavily regulated in the amount of fertilizer they're allowed to put on each acre of land, but regular humans who are not farmers are not. And so a lot of times people will over fertilize. All that fertilizer ultimately ends up in storm sewers. It ends up in groundwater, and it can cause all sorts of algae blooms, as well as just other bacteria and contamination that ends up in groundwater that requires further treatment. There are industrial pesticides that can range from things like Roundup, which again you can use in your own home unregulated, but farmers are heavily regulated. And actually, we're going to talk about it right now. And hydrofracking. Hydrofracking is something that is now banned in New York State, but used to not be. Not that long ago. But here's
What is hydraulic fracturing?
the least.
Fracking.
All right.
Since the
So I'm going to call this the least political hydrofracking video that I've been able to find. So hopefully it explains what you need to know all about hydrofracking.
industrial revolution, our energy consumption has risen unceasingly. The majority of this energy consumption is supplied by fossil fuels like coal or natural gas. Recently, there's been a lot of talk about a controversial method of extracting natural gas, hydraulic fracturing, or fracking. Put simply, fracking describes the recovery of natural gas from deep layers inside the earth. In this method, porous rock is fractured by the use of water, sand, and chemicals in order to release the enclosed natural gas. The technique of fracking has been known since the 1940s. Nonetheless, only in the last 10 years has there been quite a fracking boom, especially in the USA. This is because most conventional natural gas sources in America and on the European continent have been exhausted. Thus, prices for natural gas and other fuels are rising steadily. Significantly more complicated and expensive methods, like fracking, have now become attractive and profitable. In the meantime, fracking has already been used more than 1 million times in the USA alone. Over 60% of all new oil and gas wells are drilled by using fracking. Now, let's take a look at how fracking actually works. First, a shaft is drilled several hundred meters into the earth. From there, a horizontal hole is drilled into the gas-bearing layer of rock. Next, the fracking fluid is pumped into the ground using high-performance pumps. On average, the fluid consists of 8 million liters of water, which amounts to about the daily consumption of 65,000 people, plus several thousand tons of sand and about 200,000 liters of chemicals. The mixture penetrates into the rock layer and produces innumerable tiny cracks. The sand prevents the cracks from closing again. The chemicals perform various tasks. Among other things, they compress the water, kill off bacteria, or dissolve minerals. Next, the majority of the fracking fluid is pumped out again. And now the natural gas can be recovered. As soon as the gas source is exhausted, the drill hole is sealed. As a rule, the fracking fluid is pumped back into deep underground layers and sealed in there. However, fracking is also associated with several considerable risks. The primary risk consists in the contamination of drinking water sources. Fracking not only consumes large quantities of fresh water, but in addition the water is subsequently contaminated and is highly toxic. The contamination is so severe that the water cannot even be cleaned in a treatment plant. Even though the danger is known and theoretically could be managed, in the USA already sources have been contaminated due to negligence. No one yet knows how the enclosed water will behave in the future, since there have not yet been any long-term studies on the subject. The chemicals used in fracking vary from the hazardous to the extremely toxic and carcinogenic, such as benzol or formic acid. The companies using fracking say nothing about the precise composition of the chemical mixture. But it is known that there are about 700 different chemical agents which can be used in the process. Another risk is the release of greenhouse gases. The natural gas recovered by fracking consists largely of methane, a greenhouse gas which is 25 times more potent than carbon dioxide. Natural gas is less harmful than coal when burned, but nonetheless, the negative effects of fracking on the climate balance are overall greater. Firstly, the fracking process requires a very large consumption of energy. Secondly, the drill holes are quickly exhausted, and it's necessary to drill fracking holes much more frequently than for classical natural gas wells. In addition, about 3% of the recovered gas is lost in the extraction and escapes into the atmosphere. So how is fracking and its expected benefits to be assessed when the advantages are balanced against the disadvantages? When properly employed, this technique offers one way in the short to medium term to meet our demand for lower cost energy. But the long-term consequences of fracking are unforeseeable, and the risk to our drinking water thus should not be underestimated.
So the videos of contamination due to hydrofracking are just unbelievable. So I always show this one in class because it's pretty dramatic.
A standard kitchen match to my water, and like I said, it is unpredictable, but the methane randomly travels with the water, and sometimes it will light quite spectacularly. Just like that.
I feel like this woman gets a little kick out of this, I'm not gonna lie. So hydrofracking is banned in New York, and honestly, gas is so cheap at this point that oh, I'm totally dating this lecture. So gas is so cheap at this point, it is not fiscally reasonable to like drill down to 1,000 feet depth to really extract any of that gas. So right now it's been largely abandoned by lots of places as well. But there's definitely issues regarding groundwater contamination, not only because there are not perfect sort of lines within the wells. Like there are wells where some of those gases will escape, where some, which is what you saw right there. There are wells where some of the carcinogens will escape and then end up in groundwater. There are lots of people, though, who were very willing for a period of time when gas was over $3 a gallon, close to $4 a gallon, that they would lease their land and then just be satisfied with the idea that they would be buying water because they were able to lease their land to enter to gas and like to gas companies for a ton of money. So it's a little political, but like most things actually in real life. But right now is not allowed in New York. It was done pretty heavily in Pennsylvania for a period of years. So an example in New York of some contamination, which is pretty typical in the Northeast, is contamination by highway salt. So this is Irondequoit Bay. It flows into Lake Ontario, and this is the Bay Bridge. And if you've ever driven over the Bay Bridge in the winter, you know it gets very icy, and that's because the wind whips underneath the bridge and ices the bottom of the bridge. So for a long time, it was really heavily salted. And unfortunately, what then ends up happening is all that salt ends up in the water. Well, the Bay Bridge, in fact, this is Empire Boulevard here, and you can kayak in some of the Irondequoit Creek back in through here. If you've ever kayaked around here, there's tons of sand deposits. Irondequoit Creek is underlain by lots and lots of sand. That sand is a fantastic aquifer. And so the Department of Transportation was trying to figure out how deep the aquifer was at one point. And so what they did was they drilled into the base. This is sort of a cross section of Irondequoit Bay, where here's the Bay Bridge and here's the bay. And they drilled into the base of Irondequoit Bay to see how deep the sand layer went. And then unfortunately, winter came and it was heavily salted, and the salt is dense, so it tends to sink to the bottom, and it contaminated the sand layer at the bottom. So even though they know how deep it is now, it is almost unusable because they contaminated a freshwater aquifer with a lot of salt. So not great. Not great. And this is one of the reasons that it is so easy to get employment in areas of groundwater remediation. So these are a map. This is a map of Superfund sites in the 6-county region around Rochester. Superfund sites are sites that are so contaminated they literally cannot be used for anything until they are remediated. And all of the red circles you see here are Superfund sites that are related to soil contamination, and all the blue ones are related to groundwater contamination. So plenty of work to be had. That is the end of our section on groundwater. Just as a recap, you learned in your first assignment that porosity is the percentage of rock that is holes. Permeability is an estimate of how connected those holes are. If a rock has a high porosity and a high permeability, it is a good aquifer. It transmits water readily. If it does not transmit water readily, it is called an aquitard. In our first lecture today, we learned about the layers of groundwater as well as springs. You did a short assignment on caves and karst topography, and then today's conversation wrapped up talking about groundwater contamination. So that brings us to the end of a very long chapter 11. Thanks for sticking it out.